Hi, my name is Bradley Goforth, and I chose to do my presentation over the computational fluid dynamics of a swimmer's hand. Computational fluid dynamics is based on the Navier-Stokes equations. These equations fully govern a fluid's velocity or flow field. The Navier-Stokes equations are derived from Newton's second law and represent the conservation principles of mass and momentum. Although they were introduced around the early 1800s, the complexities of their partial differential equations have made them very difficult to solve. With the development of CFD computer software, these equations have become more practical in several situations. CFD has a lot of advantages and applications. These include the reduced cost, time consumption, and scale a simulation would require in comparison to a physical experiment. There is also an increase in possible data gathered, repeatability, and safety. CFD is also used in industries such as aerospace, automotive, biomedicine, food processing, chemical processing, heat ventilation, hydraulics, sports, and more. CFD in competitive swimming. All sports require athletes to develop their techniques for the greatest advantage in a competition. For swimmers, these athletes set out to apply forces to propel themselves through the hydrodynamic properties of water with their endurance and muscular capabilities. Effective swimmers attempt to manage the drag forces and coefficients to their advantage. To analyze their effectiveness, it's helpful to look at the swimmer's hands. About 85 to 90% of the propulsion comes from a swimmer's arms, while the most significant hydrodynamic force comes from the hands of the swimmer. The swimmer's hand will undergo a strict underwater front crawl pull style swimming cycle for more accurate analysis. For the simulation setup, there are a few necessary components. First, a professional swimmer's left hand was scanned in these four models. They were defined as adducted, abducted, spread, and adducted, spread. The stroke cycle was then divided into four phases noted as the glide, pull, push, and recovery phases. These were then split into 9 different positions throughout the stroke cycle, each with individual conditions regarding the first 3 phases of the stroke cycle. These conditions for the 9 positions had varying velocities, angles of attack, and sweep-back angles to better simulate the process of the swimming cycle. These parameters were observed from an experimental study regarding a real swimmer's stroke cycle. In the table and figures shown, you can see how each parameter changes throughout the swimming cycle and understand the angle of attack and sweep-back angle. The computational domain was then set up in ANSYS to generate meshing and fluid properties. The experimental constants were then used to frame each hand model in the domain for simulation. The flow velocity was then set to a constant speed for each hand position framed. The boundary conditions include a turbulence intensity of 1%, a turbulence scale of 0.1 meters, the temperature of 28 degrees Celsius, a water density value of 998.2, and a water viscosity level of 0.001. The simulation produced a vast amount of results. To gather more information, each test was calculated with the initial velocity as well as 2 velocities varying 0.5 meters per second higher and lower. The key results of the simulation for each position of each hand model identified the drag force, drag coefficient, and projected hand areas. With this data, there are countless conclusions to be made. The largest drag value for the adductive hand was 57.36 newtons in the pull phase. This is also where it had the highest area. This phase resulted with a mean value of 40.85 newtons. The other hand shapes each had their maximum drag force values in the push phase. The abducted hand, spread hand, and adductive spread hand had maximum mean drag forces of 43.95 newtons, 51.08 newtons, and 41.51 newtons, respectively. These maximum drag forces were all found within the higher initial velocity tests. The lowest values of drag force for each hand shape were present in the glide phase with the lowest initial velocity. This is also where each hand had the lowest hand area. The adducted hand, abducted hand, spread hand, and adducted spread hand max mean values of drag coefficient were found to be 1.96, 1.84, 1.65, and 1.75. The minimum values of drag coefficient were found during the glide phase with the highest initial velocity and lowest hand area. Here are the results plotted. It was noticed that all the drag forces varied slightly in the glide phase but increased significantly in the pull phase. Most drag forces reached a maximum in the second position of the pull phase due to the position having the largest projected hand area. After the pull phase, most drag forces declined due to the decline in projected hand area. It is also apparent that the drag coefficients increased drastically from the glide phase to the pull phase. This was caused by the different hand angles that increased the projected area of the hand. The area of highest significance seemed to be during the pull phase and less in the glide and push phase. After assessing the CFD results, it's safe to say the overall effects of hand shape, orientation, and velocity can significantly impact the propulsion efficiency of a swimmer. With a variation of hand shape, the location of a swimmer's fingers changed the values of drag force and drag coefficient. The hand orientation was important in managing drag through the angles of attack and sweepback angle. It is known that the higher or lower projected area established by these angle orientations is a direct variable when calculating both the drag coefficients and drag force. In the case of varying velocities, it was evident that higher velocities resulted in higher drag force. To have the most effective technique in an underwater front crawl cycle, it's understood that the swimmers should transition their hand shape, orientation, and velocity to the different phases accordingly.